Okay, so today we will talk about microneedles, and then we will talk about microparticle separation. Okay. So, first to talk about microneedles. When we take an injection, we typically use a capillary hypodermic needle which has size typically of the order of 1 millimeter or a few millimeters in diameter. Okay. So, that causes pain while drug delivery, and if you are using a hypodermic needle for aspiration of body fluid, then it may cause injury and in some cases infection. Okay. To one approach that have been developed to get around this problem is to develop what is called microneedles. So, these microneedles have diameter of the order of tens to hundreds of micron in size, and they stay out of the the dermis layer, okay, the hypodermis layer, and they do not interfere with the blood vessels and the nerve cells. Okay. So, that is how we are able to get painless drug delivery, and also if you are using the needle for aspirating body fluid, we are avoiding any injury. Okay. So, let us look at how microneedle works. So, if you look at this a section of our skin, this is how it looks like. We would have 10 to 15 micron of the top layer of the skin, which is known as stratum corneum, and the next 50 to 100 micron is about is called the viable epidermis, and then we have a thicker layer which is called dermis. Okay. So, and then under the dermis we have the subcutaneous fatty tissue. So, the blood vessels are found in the dermis layer. Okay. Now, when we put a large hypodermic needle for injection, it interferes with the blood vessels, okay, and it interacts with the nervous system. Okay. That is why we are able to feel the pain, and since it interacts with the blood vessels, then sometimes we have bleeding and chances of infection. Okay. Now, these microneedles, they stay out of the dermis layer, okay, and the drug is injected within the first 10 to 30 micron or about 100 micron layer at the top. Okay. So, typical microneedle thickness would be 100 micron long. So, it stays out of the layer a major part of the dermis where we have the nervous system and blood vessels. Okay. So, that is how we are able to get painless drug delivery and without causing bleeding. Okay. Now, if we, so here we look at one example of microneedles which has been developed at Georgia Tech. So, these microneedles have been fabricated using MEMS fabrication. Okay. And as you can see, these are pointed structures which can pierce into the skin, and there are some openings as you can see here, which through which the drug can come out. Okay. So, first let us look at why we use microneedles. So, typically we use hypodermic needles for drug delivery and for aspirating body fluid, and these hypodermic needles, large needles, cause pain and also bleeding, and they are not suitable for targeted drug delivery. Okay. So, for example, we want to inject a particular amount of drug at a precise location in the body, we will not be able to do that using the conventional hypodermic needle, because the sizes are of the order of millimeter. Okay, the diameter of the needles are of the order of millimeter, but we may be able to achieve that using micro needles which have the diameter of the order of tens of micron to hundreds of micron. Okay. So, the applications of micro needles are for painless drug delivery, and closed loop stimulation, okay, because so painless drug delivery is because of the size. Closed loop stimulation, meaning let us say we want to measure the reaction of a certain tissue, we subject the tissue to certain chemical or certain force, and we want to see what its reaction is, then we can put in the micro needle and integrate with the sensor to see a reaction of the tissue. So, we can with sensors to measure reaction of tissue or cells. Okay. Then it can be used for cell manipulation, to manipulate cells to move cell from one location to another. It can also be used for sample collection, okay, for collection of biosamples. Now, what are the design considerations? We look at design considerations. The most important thing is that the micro needle needs to be sharp, okay, in order for easy penetration into the skin. Okay. So, sharpness for tissue penetration, and the second thing is that the micro needle should have enough strength to withstand bending, buckling and fracture. Okay. So, strength against bending, buckling and fracture. The third important thing is biocompatibility. The micro needle need to be compatible with our body. The fourth thing is it should be able to deliver enough volume flow rate. Okay. So, sufficient volume flow rate. Now, if we are inserting a micro needle into the skin, the insertion force need to be less than the buckling force, and it should also be less than the fracture force, otherwise the micro needle will break before it is inserted. Okay. So, the condition is that the insertion force, let us call it Fi max, because the insertion force varies as it penetrates into the skin. So, we are talking about the maximum insertion force should be less than the buckling force, and it should be less than the fracture force. And the ratio of the fracture force to the insertion force is known as the margin of safety. Okay. Now, as I said, the insertion force when you are trying to insert the micro needle into the skin varies with depth. Okay. So, let us look at how does insertion force vary as the microneedle penetrates into the skin. So, we look at insertion force. The theory of skin insertion is based on the puncture toughness. The puncture toughness of the skin, which is expressed as symbol Gp. So, the puncture toughness can be expressed as the work input, the amount of work that we do divided by the surface area of the skin. Okay. So, this is the work input and this is the skin surface area. Okay. The total amount of work that we do will vary between x equal to 0. Let us say x equal to 0 is the top surface of the skin and it goes to some xi into the skin, and Fi is the force into dx. Okay. So, that will be equal to, that work will be equal to Gp puncture toughness into area, okay, as you can see from this equation, and this is where xi is the puncture position. Okay. So, from this we can find an expression for insertion force. Fix is going to be F0 into exponential x over some characteristic length scale, okay, where x here, the oblique x is the characteristic insertion length. So, what do we see here? We see here that the insertion force varies exponentially. So, as if this is x into the depth of the skin, then the insertion force is a function of x, and it is going to increase as the needle penetrates more and more to the skin, and it is going to reach a steady value. Okay. So, this is the nature of how the insertion force would vary. The work input we can find from here. So, x equal to 0 to xi F0 exponential x over characteristic length scale. So, that will be equal to Gp into A. So, you can find Fi max is equal to F0 plus 1 over x into Gpa. Okay. So, that is how you can express the maximum insertion force. So, this is a constant force, okay, and this is the characteristic length, puncture toughness into skin surface area. Okay. Now, a typical microneedle will have diameter of the order of, let us say 50 micron, and length will be about 150 micron. So, the mode of failure could be bending, buckling or fracture. Okay. So, let us look at different modes of failure. We talk about bending, buckling of microneedle and fracture of microneedle. Okay. So, first let us talk about bending and buckling. Bending and buckling of microneedles. So, the bending stiffness of a needle so let us call it K, which is given by 3 E I over L Q. Okay. So, basically this is a cantilever type of structure. The microneedle becomes like a cantilever types of structure, and this is the buckling force which is applied here, and this leads to deflection of the cantilever. Okay. So, if the length is L and I is the moment of inertia, then you can write the bending stiffness is 3 EI over L cube. So, this is moment of inertia, and this is the Young's modulus, okay, and this is length. So, we can write K as E over 4 L cube into B H cube minus B H cube. Okay. If you substitute for the moment of inertia of a rectangular cross section, then you can write the expression for the stiffness, and the rectangular cross section is it is a hollow needle, because we will have a drag present inside or the fluid present inside, and the dimension is here. B is the internal width, H is the internal width, B is the small b is the internal width, large B is the external width. Okay. So, this is actually B and this is B, and capital H is the external height and small h is the internal height. So, you can write an expression for the moment of inertia. So, that is how we get K equal to E over 4 L q into B H q minus small b H q. Okay. Now, the needle length is high compared to width. That is typically for a micro needle. So, the mode of failure, the first mode of failure is buckling, Okay. So, now to find the critical force can be found using the Euler's column model, okay, which tells that EI into d square y over dx square plus mx, which is the moment, is equal to 0. Okay. Here y is the deflection. So, as you can see here, for this cantilever case, y is the deflection, x is in this direction along the direction of the beam, length of the beam. This is the Young's modulus into the moment of inertia, and this is the moment about some x. Okay. So, that is the Euler's column model, and with a small deflection, okay, with slight deflection delta at x equal to L, which is the end of the cantilever, the bending moment m can be written as minus f into delta minus y, okay, at a particular x. This can be written as minus f into delta minus y. So, we can solve this equation, d square y over dx square is going to be f into delta minus y. Now, to solve this equation, what are the boundary conditions we have available? The boundary conditions are x equal to 0, at x equal to 0, that is the clamped end, the deflection equal to 0, and also the slope dy over dx is going to be 0. So, in that case, the deflection y will be delta into 1 minus cos kx, okay, and where k equal to f over EI square root. Okay. Now, if you apply x equal to L, y equal to delta, then you can find the different buckling modes. we can find different buckling modes. Okay. So, K into L can be written as 2n minus 1 into pi by 2. Okay. So, K into L is 2n minus 1 into pi by 2, where n equal to 1 to up to n. Okay. Now, to find the critical buckling force, and we find the buckling force for the first mode. So, in that case KL n equal to 1. So, KL will be pi by 2, and if KL equal to pi by 2, from this equation we can find an expression for F. Okay. So, that F, which is the buckling force, will be pi square EI over 4 L square. So, when we are designing a microneedle, we need to find out what the buckling force is for that particular microneedle, and we have to make sure that the insertion force does not exceed this buckling force. Okay. So, in design of microneedle, FB should be less than the insertion force. Okay. In many applications, it will be easier to use a tapered microneedle for ease of insertion. Okay. So, one such microneedle is shown here. So, this is a tapered microneedle. This is a tapered microneedle, and for the tapered microneedle we can write down E into Ix into d square y over dx square plus mx equal to 0, because the mx is varying, Ix is varying. So, the Ix for this tapered microneedle is given by the expression pi by 32 into 8 R4 minus R4 plus 32 into L minus x into tan alpha into R cube minus R cube plus 48 into L minus x square tan square alpha into R square minus R square plus 32 L minus x cube into tan cube alpha into R minus R. So, this is a long expression for the moment of inertia for this tapered microneedle. The buckling force can be found out using by solving this equation, which is given by E over 40 pi L square into phi pi 4 divided by 2 into R4 minus R4 plus 20 pi square plus 5 pi 4 into R cube minus R cube into L tan alpha plus 30 pi square plus 5 pi 4 to R square minus R square L square tan square alpha plus minus 120 plus 30 pi square plus 5 by 2 pi 4 into R minus R L cube tan cube alpha. Okay. So, this is the expression for the buckling force for this microneedle. So, L is the typical length of the microneedle, capital R is the outer radius of the microneedle at the tip. So, this is the tip, So, capital R is the outer radius and small r is the inner radius and alpha is the taper angle. Okay. So, with that you can get an expression for moment of inertia and the buckling force. Okay. Now, the fracture force, you can write down the expression for fracture force for a hollow tapered needle. The fracture force is derived from thin cell model, meaning the tip radius is greater than 10 times the wall thickness. Okay. So, in that case the fracture force Ff is given by 2 pi RT into T sigma critical into sin alpha. Okay. So, here this should be the tip radius and T should be thickness of the wall, because we are talking about a hollow microneedle, and this is the critical stress, okay, in fracture, right. So, we also have to ensure in the design that the fracture force is is not exceeded by the insertion force. So, the insertion force has to be less than the buckling force and it also has to be less than the fracture force. So, the insertion force has to be less than the fracture force. So, now let us look at the flow characteristic of a microneedle. So, we look at the delivery with hollow microneedles. So, we one of our goals while designing microneedles from the perspective of flow is that the pressure drop has to be as small as possible, okay. And for that we need the inner bore of the microneedle has to be as large as possible to reduce back pressure, okay. So, we need the channel inside microneedle as large as possible to minimize pressure drop, okay. And so that would allow maximum flow rate. So, the delta P is given by F RE into eta L divided by 2 ds square into velocity, okay, where FRE for laminar flow, as we are talking about microneedle, has a value. So, FRE is between 50 to 60, okay, and eta is the dynamic viscosity, L is the length of the microneedle, dH is the hydraulic diameter, which is 4 into area of cross section divided by the weighted perimeter, and U is the velocity, okay. So, these are different criteria based on which microneedles are designed. One, from the mechanics point of view, the insertion force has to be less than the buckling force and the critical force, and in order to supply delivery with certain flow rate, we have to ensure that the inner bore of the microneedle is as large as possible, so that the back pressure is less, okay. So, with that we complete our discussion on microneedle. Let us move on to microparticle separation. So, we talk about microparticle separation. Microparticle separation has different applications in biomedical and in chemical analysis. It also has applications in chemical industry, mineral industry, and many other applications that it sees, okay. So, let us look at the principle of different principles of microparticle separation. So, as you can see here, the microparticle separation is broadly classified into two categories. One is the passive separation. The passive separation mechanism does not use any external energy, it uses the interaction between particles and the flow to separate particles based on physical properties. Then we have active separation mechanisms which makes use of external energy and uses the external energy like electric field and magnetic field to separate particles. Okay. Now here you can see there are different principles in passive as well as in active separation methods. In passive separation methods we have pinched flow fractionation, inertia and Dean flow, and we have deterministic lateral displacement or DLD, and then we have biomimetic or bifurcation law, cross flow filter, and then hydrodynamic separation. Okay. And in active separation method we have dielectrophoretic, magnetic, optical and acoustic. So look at each of these techniques in detail. So this is the pinched flow fractionation technique. As you can see here, we have a sample that contains the particles, and here we have a buffer which does not have any particle, and this sample is focused by the buffer stream such that the particles get aligned to one of the side walls, and this is known as the pinch segment. So this has a lower width of the channel, and as the pure fluid focuses the particulated fluid, the particles get aligned to this side wall, and as we know the particles have a tendency to flow along the streamline passing through their center of mass. Okay. So the particles have a tendency to flow along the streamline that passes through its center of mass. Following that principle, for a smaller particle, the streamline passing through its center of mass will be closer to the wall. Okay. So it will be closer to the wall, and for a larger particle the streamline passing through its center of mass will be away from the wall. Okay. So the different size particles follow the corresponding streamlines passing through their center of mass. So we would have after the pinch segment, when the flow gets into a broadened segment, so this basically amplifies the separation distance between the streamlines, then the smaller particles will go towards the closer to the wall, whereas the larger particles will go towards the center. So in that mechanism we would be able to separate particles of different sizes across the channel. Okay. And this is one important formula that is used for design of pinch flow fractionation channels. So here y0 is the position of the particle center at the outlet. Okay. So at the outlet, let us say this is the position of the particle which is y0. So y is in this direction. So Wp is the width of the pinch segment. So this is the Wp, and W0 is the width of the outlet. Okay. The total width here is the W0, and d is the diameter of the particle. So this is how these parameters are related. Okay. So y0 is Wp minus d by 2 into W0 by Wp. So this is the formula which is used to design pinch flow fractionation networks. Okay. Next we move on to Dean drag force. So the Dean drag force mechanism is based on three different kind of forces. Here as you can see we have shear gradient induced lift, we have wall induced lift and Dean drag flow. Okay. Now when particles move inside a fluid in a channel, the difference if a particle is moving through a channel, the difference between the particle velocity and the liquid velocity is higher closer to the channel as compared to that of a particle closer to the center. Okay. So that generates a force closer to the wall, okay, and that is known as the shear gradient induced lift. So there is a lift force closer to the wall in the direction closer to the wall, that is known as shear gradient induced lift, okay. And there is a second force which because the speed of the velocity of the liquid is maximum at the center as compared to that at the wall, there is a lift which is going to be from the wall into the center of the fluid, and that is known as the wall effect induced lift, okay. So as you can see here, this is there are two forces, one is shear gradient induced lift and the second one is wall effect induced lift, okay. Now there is the third force which is called Dean drag flow. So the net effect of these two lift forces is outward, okay, so it is going towards the channel wall. Then because the speed of the liquid is higher at the center, the liquid tends to move outward closer to the channel wall, and to satisfy mass conservation the slow moving liquids come back towards the center. So as a result we would have two opposite vortex at the top and bottom walls, okay. So these vortexes are called Dean vortex, okay, they are called Dean vortex, and the direction of the drag force that is induced because of this Dean vortex is towards the center, okay. So the net lift force is acting towards the wall and the Dean drag is acting towards the center, and if you take a ratio of lift force to drag force it will vary as this, okay. So this is the ratio of the lift to drag force, which is 1 over delta into A by dH whole cube, okay. So A is the size of the particle, the radius of the particle, and you can see that the ratio is a function of the third power of the particle size. So based on this mechanism, particles of different size will be subjected to different ratios of lift force and drag force. As a result they will be separated in a direction from the center to the wall of the channel. So as you can see here, in this case there are a particle mixture is included infused into the channel at these inlets, and as it moves through the spiral channel, because of the competition between the Dean drag and the lift force, you can see that the larger particles which have higher lift force as compared to the drag force gets towards closer to the channel as compared to the smaller particles. So that is how they are going to be separated based on size. Next we will look at a technique called deterministic lateral displacement or DLD. Here we have in the channel a post, an array of posts that are sticking from the channel, okay, and the deterministic lateral displacement is based on the principle of steric hindrance. Steric hindrance means the wall is trying to apply a force on the particle to escape from one streamline to get into another streamline, okay, that is known as steric hindrance, okay. If you look here, there are different rows here, and as compared to the first row, the second row is offset by a distance delta lambda, okay, and the angle between the center, the vertical line through the center of the first row, let us say this post, and the second row first column post is theta, okay. So the second in the second row the corresponding post is displaced by delta lambda, so it creates an angle theta at the center of the first post, okay. So delta lambda is going to be lambda into 10 theta, where lambda is the separation distance between the rows and columns. Okay. Now the first row is going to be repeated after nth row. So the n plus 1th row, the first row and the n plus 1 row which is here, they are the same, they have same position, but the others each subsequent row are displaced by delta lambda. Okay. So that is the arrangement, that is the geometry. Now if you look at the mechanism, between two adjacent posts, let us say this is post 1 and this is post 2, we have different streamlines. Okay. So in this case we have 1, 2, 3, 4 streamlines. Now if you look at the stream between the surface and the first streamline, the width is beta. Okay. And this beta is expressed as square root of n over 3 into d over n, where n is the period of the array, meaning the first and n plus 1th row have the same configuration. Okay. So that is what we have seen, the first and the n plus 1th row have the same configuration. So the geometry has a period of n. Okay. So the geometry has a period of n, and so that is how we can express beta in terms of n and d. Beta equal to square root of n over 3 into d over n, and d is the diameter of the particle. Okay. So d is the diameter of the post. Okay. D is the diameter of the post, so we can find beta. Now if the size of the particle is less than beta, less than this characteristic length that we have just defined, then it has a tendency to stay within this blue stream. Okay. So it will follow within the blue stream in a what is called a zigzag path. Okay. So the particle will move almost straight, but in a zigzag mode. Okay. Following this red path. Okay. So the red particle has a size less than beta, and so it follows the zigzag mode. If the radius of the particle is greater than beta, then it will move from this stream into the next stream. Okay. So as you can see along the green line, the particles having radius greater than beta, it will get displaced into the next streamline, and it will keep on getting displaced, so that it gets into the displacement mode and the particle will exit there. Okay. So based on the particle size, the smaller particles will follow the zigzag mode and the larger particles will follow the displacement mode, and that is how we can separate them. Okay. Now the next principle is based on biomimetic, or it is also known as bifurcation law, and this was first reported by Wai-Shifeng, who is the father of modern biomechanics. And what he told is that a cell have a tendency, let us say cell is flowing along a channel and it encounters a bifurcation where the flow rates are different. So the flow rate here is higher, flow rate here is lower. The cell has a tendency to get into the high flow rate channel. Okay. So based on this principle, the particles and liquids can be separated. So as you can see here, one such device has been fabricated by Maven et al, and it was demonstrated that blood having the cells and the pure fluid which is the plasma, by establishing the channel geometry such that the flow rate in this direction is higher as compared to in the lateral direction, the cells could be collected here in the high flow rate channel, they can flow and can be collected at this outlet, and the plasma which is particle free fluid can flow in the side channels and be collected at these outlets. Okay. So that is how you will be able to separate cells and plasma from blood using the biomimetic or bifurcation law method. Okay. So next we move on to cross flow filtration. In cross flow filtration, we have so as you can see here, let us say the particles sample comes in here, and the difference between the cross flow filter and the dead end filter is that in cross flow filter the filtration occurs in a direction perpendicular to the normal to the flow direction. Okay. So that is how the pores of the filter do not get clogged and continuous filtration is possible. So in this case you can see that as the sample containing particles comes in, between the gap between the post on the sides of the channel, the pure fluid can escape where the particles cannot escape. So the pure fluids escape through the post on both sides, and the pure fluids are collected here and the particles are collected here. Okay. So that is the principle of cross flow filtration. This is another work that has been reported. As you can see here, the sample comes in here with different size particles, and there are membranes of different size. As you can see here, the red is 5 micron membrane and the yellow is 2 micron membrane, and the green is 400 nanometer membrane. Now as the sample comes in through this filter, since it has 5 micron size filter, the particles lower than 5 micron size will get filtered and come up. Okay. And particles that are greater than 5 micron will come out through the outlet 1. Similarly, then next it will go to the 2 micron membrane, then particles of size less than 2 micron will come up, and the particles less than 2 micron will come in outlet 2. Similarly here, in particle 3, what will happen is the particles of less than 400 micron will come here, and the particles larger than 400 nanometer will come out in outlet 4. So that is how we will be able to separate different size of particles in a sample using cross flow filtration. Next we talk about hydrodynamic technique. In hydrodynamic technique, the particles mixture comes from the channel here, and if you can adjust the flow rate ratio of this branch channel to this main channel such that the stream width here, okay, the stream width that is escaping into the side channel is greater than the radius of the largest particle that is present in the sample, then most of the particles will get into the side channel. Okay. Even the larger particle will get in the side channels, and some that are present here will escape straight. Similarly, if we adjust the flow rate ratio such that the stream width here is less than even the smallest particle that is present in the sample, then all the particles will go into straight. Okay. Now if we can adjust the stream width such that it is more than the radius of one set of particles, whereas it is less than the bigger particle, then selectively particles can be collected at different outlets. So that is the principle of hydrodynamic filtration. So with that let us stop here. We will continue our discussion on active separation in the subsequent lecture.